All right, everyone. So today we jumped headfirst into stoichiometry. Second period, we didn't actually do this full demo, but I did end up doing it for fourth. So if you want to check out a video of the full balloon demo, it is posted on Instagram, but we'll do it later in the week again as well. So for that demo, remember we were highlighting this idea of that perfect mole ratio, just like we were doing in the lab, seeing that a 2-to-1 ratio of hydrogen to oxygen should be the best, should give us the best result. So we made 3 balloons of approximately equal size, one of them containing a 1-to-2 ratio of hydrogen to oxygen, the other one a 1-to-1, and the last one a 2-to-1 ratio, matching that perfect mole ratio. And we saw that the booms got better with the higher hydrogen content, with that final one having the really nice big boom. So you can check the video out on my Instagram, and we'll do it again in class as well. We then moved into looking at the math of it and forcing ourselves to really play with the math. So we played with this idea of making s'mores. And so we look at my recipe for a s'more. Remember, you make your s'mores however you want, but for this, use my recipe, just to show ourselves we just can do the same mechanics every single time, starting with what we have and aiming for what we want. Then we really rapidly went into actual stoichiometry. Remember that using stoichiometry is using this mathematical technique to use the mole ratios to understand those relationships between those coefficients, those molar values of our reactants and products in a chemical reaction. And the mole ratios, we use those as conversion factors. So in this example, we have a generic 2A plus 3B makes 2C. We have 3 different conversion factors we could create, and we could use them either way with A or B, A on top or B on top for the AB conversion factor, whichever one we want to use. Then moving forward, we started doing some examples. So this first set were all just very straightforward mole-to-mole conversions, as simple as it can be with only one conversion. And here we're using that mole ratio as our conversion. So all of these reactions, they're following the hydrochloric acid and sodium carbonate reaction. And we see that for all of these, we're starting with our 3 moles of HCl. And so this just shows the math, how you go through. Start with what you have, set up your conversion factor. In this case, each of our conversion factors is a specific mole ratio. In part A, we're relating moles of HCl to moles of NaCl. Get the units in the right spots, cancel your moles of HCl, and you get the appropriate number of moles of NaCl. Remember, we talked about that you must put in, like in this example A, you've got to put in 2 moles of NaCl to 2 moles of HCl. You cannot simplify those. If you put 1-to-1 or leave it out because it is just 1, that is 100% inaccurate and inconsistent. You need to have that mole ratio values in your conversion factor match the values that are in the chemical equation. Then we moved forward and looked at some more advanced problems, where instead of just using the mole-to-mole ratio, we're going moles to grams or grams to grams. You could go grams to moles. You could go concentration, whatever, right? We can go kind of anywhere we want as long as we get through the mole ratios in the middle. So here, this is that hydrogen-oxygen reaction that we used with the balloons. Remember, we are always starting from a balanced equation. That is how we get that special, perfect stoichiometric ratio of all of the compounds, and those are the numbers we get to use in our mole ratios. So we see that each and every one of these has that mole ratio in the middle. Us to the next one we were talking about, that no matter what you're starting with, you have to go through a mole ratio. If you're going to transfer from one species in a reaction to another species in a reaction, you have to go through that mole ratio to communicate between the two, meaning you have to get to moles before the mole ratio, and you will come out with moles of the other thing on the other side of the mole ratio. Beyond that, it depends on the problem. What are you given? What are you asked for? You might do a whole bunch of other conversions, but you're always coming through that mole ratio in the middle. So here we saw an example using molarity, right? So we need to start with milliliters, convert to liters, then liters to moles using our concentration. Then we can use mole ratios to get to the moles of our other thing, of our sodium carbonate in this example. Then we can use molar mass to get all the way to grams. So you see now we have these 4 conversion factors, line them up, knock them down, cancel your units, put the math in, and you're good to go. We also talked about how you can use just kind of common sense and looking at the relative sizes of all the numbers to make sure that your answer is in the right ballpark, right? We're starting with a number in the hundreds, dividing by thousands. That gets us to about in the 0.1s. Multiplying by a 1-ish, dividing by a 1-ish, we're still in the 0.1s. Multiplying by 100, meaning our answer should be somewhere in the 10s, right? Just to give us a ballpark, and we have an answer of about 20, so that's perfect. We're in the right range. If we had an answer of like 20,000, we would know we had done something wrong. All right. We looked at another quick example, but don't stress about that. Remember, the packet has a bunch of extra practice and instruction. Get your lab write-up done and turned in, and we will be looking at titration next class. Have a wonderful weekend. So yeah, and that's